Let's talk about spatial data. So today we're going to focus on the third of the three major data types, not tabular data, not network data, but spatial data, where we have information either sampled regularly or irregularly at different points in space, or just a purely geometric information about the shape of some spatial regions. So we've already talked about four ways of arranging data in position-based layouts: expressing quantitative attributes directly, separating into regions and ordering and aligning with, say, categorical data. Now we're going to talk about just using given spatial data. So if we're going to use given spatial position data, when would we do that? Well, first of all, we have to have it. The data set must contain spatial attributes, and they need to have primary importance. That is, we want to say, do our tasks revolve around understanding spatial relationships? And if so, we probably do want to use that given spatial position data in our visual encoding. In this lecture, I'm going to focus in particular on geographic or cartographic data. So geographic maps. With geographic maps, what are we doing? Well, from an analysis point of view, we have these polymarks, right? We have these areas. They have 2D shared boundaries because they aren't necessarily exactly aligned to horizontal or vertical positions. And what are we doing? Well, we're encoding using the position and order channels. We're encoding that given spatial data. Now, we can't use other channels to show other attributes because a bunch of them are locked down as unavailable because of these two-dimensional shared boundaries. So things like size coding or orientation or symbol shape, those are locked down, so those are unavailable for use. Now, the cartographic word for maps that we're going to really focus on in this lecture, visualization-based maps, are thematic maps. They call them that because they want to focus on this idea of a theme, namely showing the spatial variability of some attribute. So a thematic map is where we're combining some reference geographic map with tabular data. These are typically straightforward, simple flat tables. So the idea is that there's two things we want to join in some way. There's a geographic region which is a shared boundary polymark, right? Like provinces, countries, where we've got these outlines. We might also have point marks if, for example, we're just trying to show cities or something like that using, and all of these are typically in a two-dimensional latitude, longitude coordinate system. But we're also going to have the idea that a region is some sort of unique categorical key attribute in a table that we can use to look up a value. So region as geography, as geometric boundaries, and region as a unique ID we can use as a key to look up some values. So in today's lecture, we're going to focus on four major idioms: choropleth maps, symbol maps, cartograms, and dot maps. So what's a choropleth map? We've already seen quite a few of these so far. And that's our situation where we use our given spatial data. We do want to understand spatial relationships. And as I just said, we have not only the geography as geometry, but we have a table where for each region that we have a shapefile for, we have a quantitative attribute. And what are we going to do? Well, we're going to use those polymarks, just like the base map, to actually encode that region. And then we're going to encode a quantitative attribute with color. In this particular example, it happens to be a sequential segmented color map, but we could do it with any color map we want. So the given spatial data is encoding the position and the order, and then because these are shared boundary polys, what's unavailable is size coding or orientation coding or shape coding. Now, in this kind of a map, we just have the one mark type polys, just like the original base map. So beware, it's tricky. This is a particularly snarky XKCD comic about it, but population maps often just show where people live. So it's a spurious correlation. All kinds of attributes will just show here's where people live. So be careful of when should you normalize. If you're showing data about people, and a lot of the data that we gather are, think about when to normalize by population density. So instead of just raw data values, use normalized data values like, mean family income or unemployed people per 100 citizens. So be very aware of thinking about normalization when you're using choropleth maps. And actually think about normalization all the time, not just when you use maps. This question of when is it safe to use an absolute count versus when should you use some sort of normalized data, relative data, that's something you should always think about in visualization. And it's a really common error to forget to normalize. So it's absolutely on the table of something you got to worry about with maps, but do think about this in general as well. So what are the recommendations for choropleths? Well, use it when your central task is understanding the spatial relationships. They're showing just one attribute at a time. There are more sophisticated ways of dealing with multi-attribute data, but a choropleth is just one single attribute. Be very careful to think about normalization and when is that appropriate and necessary. Also, be careful when choosing colors and bins. So um, there is quite a lot of nuance in binning, deciding the right number of bins, and what is the color coding. We talked a lot about color in the color lecture, but I'll just point out that deciding how many bins you want to show is an interesting and challenging question with maps, just like it's an interesting question with, say, histograms. So that choice of if you're going to discretize into a finite number of bins, what should that number be? That can be very tricky and it can really change what kinds of patterns people see on the map. Now, another important thing is the best case for chloroplaths is when the regions are roughly equally sized. If there's a lot of variability, then we can run into challenges. So some of the pros and cons of choropleths, well, for pros, they're very easy to read and understand. They don't need teaching. People just get that you've encoded something with that color. So very well established, no learning curve. Also, it's often the case that the geographic regions that you want to encode with color are, in fact, the geographic regions they used to gather the data in the first place. And when that's true, that's a very good match. You don't have to worry about these sort of interpolation issues or sampling issues or anything else like that. Okay, what's bad about choropleths? Well, one thing is we've talked a lot back when we started talking about marks and channels that the position channel is the most effective visual channel. Now, you're just showing geographic location with that. So if understanding geographic patterns is completely central, then maybe this is a good choice. But if it's more of a peripheral thing, it could be that you might want to pick some other attribute to really focus on rather than using geographic position for that. So that's a judgment call for a designer. Now, as I just alluded to, there's some issues here, which is that how visible is the color coding? The visual salience of the color coding really depends on the size of the region. And what if you have a small geographic region, but there's something really important going on there? Well, it's going to be much harder to see because large regions are going to be actually just more pixels on screen than smaller. Our ability to perceive color very much depends on the size of the region. So things could appear to be unimportant and you can maybe barely see it, but maybe that's actually a really crucial attribute value. So that's an issue with choropleth maps. Also, as I alluded to, also the color palette choice does have a really large influence on the result. So what's another thing we could do? Well, we don't have to color code the region. We could add another layer of symbols. So symbol maps are a whole family of idioms where we've got one symbol per region that's used to represent the aggregate data for that region. It could be a point mark, it could be a glyph. So what we're doing now is we're adding a second mark type. It's at the same level. It's not a multi-level thing, but there are two different mark types at the same level, those base polys and our new symbols. So with the simple map, you do keep that original spatial geometry in the background as polys, but then you add one symbol for each of those regions, and you are size coding it. So it could be 1D size or 2D size. It's normally a quantitative attribute. So what's free here is you could shape code that symbol. You could color code it. If it's an asymmetric shape, then or a glyph, you could have orientation coding. These have a lot of different names. Sometimes they're called proportional symbol maps or graduated symbol maps. These are often a good alternative to choropleth maps. So here's two examples of a point mark based symbol map. So on the left, we've got state population. Notice how these are size coded circles. Now, notice how these can overlap each other, right? These are on top of each other. These are not shared boundary marks. They're not polys. These are just points, and they can occlude each other. And they do in many regions, like the U.S. Northeast. Then on the right, we've got a different symbol type. We've got these triangles rather than the circles, so we do have some kind of ability to see orientation. This is a map of Christmas trees, so they pick something a bit evocative of a Christmas tree. And again, notice how these are overlapping. Here's a couple examples of symbol maps with glyphs. So these more complex glyphs that are made of multiple marks inside of them. So, one example of a glyph is just a teeny tiny bar chart on the left. Here we got pie charts on the right. Um, and these are very commonly used in symbol maps, little charts trying to show, I mean, not a hugely complex thing. You would not make a, 50 bar glyph or pie chart. But if you've got a relatively small number of attributes, this can be very reasonable. So far, we saw glyphs where the symbol was just put right in the middle of the region, but you don't actually have to do that. For example, here's an interesting variant of symbol maps called necklace maps, where there's a fairly complex algorithmic computation of where to put that symbol so that it looks like it's visually connected to the region, but actually it's on this circle outside of that region. Um, Notice how, in this case, they're carefully positioned to completely avoid overlaps, as opposed to the symbol map on the right, the traditional one, where in fact there is a bunch of overlap, and the Luxembourg is right on top of Belgium, is on top of the Netherlands. So we can solve that problem, for example, with the symbol map algorithm. So there's many other variants as well. These are just a few. So what's good about a symbol map? It's pretty intuitive, and it solves that region size problem. Notice how on that previous version we saw that even small regions like Luxembourg were able to actually have highly salient data. Um, so because the symbol mark actually has a size that's coded to the value of the attribute, not just inheriting that given spatial dimension. Um, so typically with marks, you've got a size-coded symbol. With the glyph, you often have the glyph itself being a uniform size, and then within the glyphs, when you have marks representing specific values, those are the ones that would be size-coded. Okay, so what's bad about those symbol maps? Well, their strength is also their weakness. You can have overlap. So the symbols could overlap on top of each other. They might actually get in the way of even being able to perceive the region boundaries. And, complex glyphs might require some sort of explanation or training. All right, another family of idioms for looking at geographic data is cartograms. So cartograms are a situation where we're changing all of the polymarks on the map at once, simultaneously. So we have only one mark type. We're replacing the old polytypes with new marks. Now you might think, wait, that's a shared boundary. We aren't supposed to change things. But you can't change a single mark on its own, but you can change all of them at once. So the original map polys have these shared boundaries, and in fact what we're going to do is compute a new set of interlocking marks, interlocking polymarks, also with shared boundaries, and we're going to try to preserve relative position, that is, order, as much as possible from old to new. Now there's a lot of variants of cartograms, and there's different constraints. In some cases, you want to preserve the shape as much as possible, so you would take a quantitative attribute and actually size code, but preserve the shape. Or maybe we try to regularize so that everything's actually the same shape for every region, and then we color code like a choropleth. Or maybe we regularize both size and shape. So let's look at some examples. So the most classic cartogram is this contiguous cartogram. So still have polymarks with these shared 2D boundaries. The fancy name for these is sometimes area proportional continuous cartogram. And what you do is you derive a new set of polys. They're going to interlock together like the old ones, and you're going to use that quantitative attribute and size code each region. So you're going to maintain order. You're going to make sure that stuff to the north is above, stuff to the south is below, east and west. So you're going to have this quasi-geographic positioning where you keep the order, but the actual position can change. And then also the orientation and the shape are changing as well under algorithmic control, so you can't encode anything else with them. So here you see a couple examples. On the right, we've got the greenhouse emissions versus the child mortality. And this is a world map, so you probably are aware of what the base polys would have looked like. And then we see two different kinds of distortions. And we're noticing, a lot of anti-correlation, right? Negative correlation between big for greenhouse versus small for child mortality or vice versa. Um, Notice how on the bottom here in red and blue, we've got a US election cartogram. Um, so what's going on? How might you actually do this? Well, you have some quantitative attribute as the input, which is the target size, and then you can have an algorithm that's trying to keep as much as possible, but not completely, the shape, the position, and the orientation as close to that given spatial data as possible, even while changing the size. And so the requirement in the case of continuous cartograms is keep the order, but and also make sure to keep the shared boundaries contiguous and preserve the shape as much as you can. Well, what else could we do? A so-called Dorling cartogram or a circle cartogram is where you actually throw away the complexities of the shape. You regularize each shape, each region down to just a circle. So these are now point marks. They have shared 2D boundaries, but we're basically now doing essentially a circle packing. So we want to encode that quantitative attribute with two-dimensional size, and we're trying to encode the relative location. We still want California on the left and Florida down below and New York up top. So those relative locations, that is, the order is you're preserving that. What's not available below is position because the algorithm is moving things as need be. It is still trying to maintain these constraints, which is all the circles need to touch each other. So it needs to be a circle packing. We can't reorient because circles are symmetric. We can't have a different symbol because definitionally, Dorling cartogram is circles. You're definitely free to color code, as this example shows. So it's like we're doing circle packing with quasi-geographic position constraints. You're trying to do as much as you can to preserve the position, but the only thing you're really guaranteed to preserve is that order. There's other things we could do as well. We could regularize not only the shape, but also the size. And so grid cartograms or equal area cartograms are this approach where you say, okay, again, we're going to derive a new poly. It's going to have 2D shared boundaries, but I'm going to fix the shape and I'm going to fix the size. And thus also we're fixing the orientation because they do have shared boundaries. So just like before, we have this idea that that position is certainly in use. We can't use it to encode anything else, but it's not a guarantee of representing the given spatial data. But we are keeping that ordering, the north-south, the east-west ordering. And you can color code just like with choropleth. Now, these have a lot of different names. Sometimes they're called grid maps or mosaic cartograms, a pseudodemos cartogram or geofacet or geogrid or tile grid map or tile map. But once you know what this form is, you're going to start to see them actually quite a lot, particularly for election results. These are often very popular for that. So here on the upper left, we have circles. In the middle, we've got squares. Then we've got hexagons. So these hex grids are particularly popular because they do a really good job of tiling the plane and using up space with something that seems to fit together a bit better than the squares. It's not just for US maps. I've been showing you a lot of US election results, but here's an example of a London map on the right side. Okay, so what else could we do? Well, we could even get particularly fancy and start thinking about cartograms at multiple levels. So here's an example where they've built a two-level interpretation. At the top level, we have these polys, these shapes representing states. Um, and just like the other cartograms, right, we're trying to preserve, preserve position and shape as much as we can. But we're definitely worrying about the order so that people can even understand and interpret this. So the top level has these polymarks, but the bottom level has unit marks. It has these uniformly shaped squares. And what that gives you is countability. In this case, what they're showing is votes. Um, so by having these unit marks as the lower level structure and the state polys as the high level structure, you're able to actually literally count things like votes. Um, and like the other cartograms, these also have shared 2D boundaries. Now, it's obvious that they do with the example on the left, where you have all these states touching each other. I would actually argue that what's going on the right is interestingly the same. Um, they're using white space in a very deliberate way that lets you actually directly count off the population density because the more white space there is, the fewer people live there compared to the size of the spatial region. Um, so even though these don't seem to be touching at first glance, I'm going to count these as being touching because there's little blocks of white space in between those. So that's a counterexample to most of the time where I say you need to be having marks actually touch each other to count as shared boundaries. But in this case, there's some implicit little white boxes as well. So, what are the pros and cons? Well, for contiguous cartograms, they can be intriguing. They can be engaging. People look at them and say, hey, what's happened? Suddenly this thing is big. So, the very best case is where you have strong and surprising size disparities in a way that's actually noticeable. Now, the downside of a cartogram is you have to know what it looked like before you distorted the shapes. So the viewer needs to have very substantial familiarity with that original data set, and they're comparing what they see to what they would hopefully remember having seen before. Um, Now, there's some ways to actually try to support that. For example, you might have an animated transition from the base to the cartogram and back again. And so often you'll see these animation loops of going back and forth. Um, or you could have side-by-side views of the original right next to the cartogram. That's also quite frequently done. Another issue is the more you have these disparities in size between the original polys and the new ones, there's more and more distortion, and that can be problematic. It can just be flat out ugly or weird looking, right? Just aesthetically displeasing. And also, the more distorted it gets, the more you might have difficulties in even recognizing what the mark is. So there's definitely some boundaries of just how far can you resize and have it still be recognizable. And certainly, if your goal is precise accuracy of decoding what got encoded, well, this is not going to be that same level of precision as something like, look, this bar is, 5% taller than that bar. You can easily notice that. You might not be able to even tell a 5% difference in size between two cartograms if it was contiguous. So it's much more for focusing attention on a few particular outliers and not so much precision readouts. Now, for the non-contiguous cartograms, well, the good thing is people have an easier time understanding them. These stylized marks are typically a lot easier to understand than the distorted shapes that nevertheless still touch. And these can be a really good base for combining, right? The equal area versions that have those uniform shapes and uniform sizes can be particularly easy to work with. And the equal area approach can really mitigate that size disparity problem. So um, it, but particularly the choropleth size disparities might be an issue in just standard choropleth. But if you have an equal area cartogram, well, then you don't have that size disparity problem because everything got regularized to the same size. So what are the downsides? Well, they still do require some level of familiarity with the original. Not as much as the others, but some. You might need to explain this idea that, the position doesn't quite mean what you think it might mean. So it might need some explanation. Uh, and one thing is there might be some pretty substantial distortions if the original regions have really different sizes and then you're normalizing them all to the same size. That could really start to distort things substantially. All right, let's talk about our fourth family of approaches, and that is dot maps. So Let's start with the obvious ones. I'm going to call these one-to-one dot maps. And it's where there's a thing and it's got a position and you show that. So the actual location of an item or a feature or a phenomenon, something that can be sort of localized down to a specific x, y, lat long coordinate. So you're going to position code them by that given spatial data. Confusingly, sometimes these are called dot density maps, but I'm going to focus on calling them one-to-one dot maps. So a point is representing a specific item. You're free to color code, size code, simple shape code. Um, Now in this case, like with the symbol maps, now we have two mark types. There's those base polys, and then there's these points representing specific locations. So two mark types, the dot points and the region polys. And of course, without the region polys, well, you wouldn't know what the dot points meant, right? So that base map is important. And so these are particularly good when you're trying to really understand the spatial distributions of things, find patterns, maybe find clusters, find outliers. So this particular case is showing the nearest burger chain, whether it's like, what's the nearest one in this region? Is it Burger King? Is it Dairy Queen? Is it Jack in the Box, McDonald's, so on? What else could we do? Well, there's a different way to use dots on a map, and the naming is quite confusing. I'm going to call these dot density maps that are many to one. So many to one dot density maps. And in this one, the dot does not mean here's where something happened. Instead, what they're doing is they're saying, I'm going to try to show you a distribution by having different densities of equally sized dot marks. So within some region, you're going to either have a few dots or many dots. But it's not about that's where the thing happened. It's about let me try to show you a pattern within this larger region. And so the tricky thing is one symbol represents many items. All those dots are the same size and shape, and that means you can't use the size and shape and orientation channels. But the key thing is the location within the region is random. It's not meaningful. Um, so certainly you can't position code anything else. This is showing you with position where these things are. It's free to use color if you like. Sometimes these are called dot distribution maps, which I think is also possibly a better name. Um, but be aware that some people call these dot density maps, whereas sometimes other people use the word dot density for the earlier one-to-one dot map we saw. So this can be very confusing, and you have to check carefully to make sure you understand. If it says something like here, where we have one dot is 50,000 people, well, then that's a dot density map. So here again, we do have two mark types. We've got the base polys and then these points. So you can see spatial patterns and clusters here, but be careful. These are high-level spatial patterns that you can only count on at the region level. So you can see one region compared to another region, but be careful to not think that the dot means a thing happens at that exact location. So the pros and cons of dot density maps. Well, one-to-one dot maps are quite easy to understand. They're actually very natural. And they do avoid that non-uniform region size problem with a choropleth because you've got dots. You don't have polys. You're just using dots, so point marks. Now there's some cons. Just like choropleths, you've got these normalization questions. Are you just showing where people live? So that same population density problem that needs normalization absolutely needs to be addressed with dot maps as well as with choropleth maps. Now, dot maps are for getting general senses of things, and so for the dot density maps, it can be difficult to extract the exact quantities. People can get a sense of density, but you don't want them to have to start sort of counting the dots within the region. That's usually not the kind of perceptual behavior we like to see. Now, there's some practical issues here. If you're using dot density maps, these can get to be very computationally expensive very fast. If suddenly you're drawing 100,000 points, that can start to be a problem with some lag. So be aware that there can be computational challenges. But I think even the bigger issue with dot density maps is that those many to ones could really confuse people because it's very tempting to think that the location of the dot means something. So it's easy for people to assume that what is actually just trying to show you density is in fact showing exact location, even though that's not the case. So we've talked through a few different possibilities for thematic maps, four in total. And I want to point out that you can mix and match these. I mean, we've already seen that. Choropleth can be combined with anything else. So cartograms can be used with other approaches, right? You can have a cartogram that has choropleth color coding. You could have a symbol within a choropleth region, or sorry, a cartogram region. You could add dots with a dot density map or just a one-to-one dot map in a cartogram region. Now you have to be particularly careful with the cartogram if you're trying to actually encode exact geographic locations. So that might be trickier. But for a dot density map, you could have a dot density map on a cartogram region. The other thing you need to be careful about is probably quite tricky to use a symbol map and dot maps at the same time because understanding is a mark, a symbol, or one of these dots could be quite ambiguous about whether it's an aggregate mark showing data for that whole region, and that's what a symbol map is showing, or a one-to-one dot, which is a meaningful position, or one of these many-to-one dots where it's a random position and you're trying to represent many items of data with that single dot. Okay, so let's move on from families of visual encoding approaches to just thinking about the entire idea. But wait, how do you draw that map in the first place? And that brings us to map projections. So a map projection is some mathematical function that maps from the three-dimensional surface of the Earth, which is a curved surface in three-dimensional space, onto a flat two-dimensional plane for a flat map. Now, the tricky thing is something has got to give. So if you're projecting from a sphere onto a plane, you can't have that be perfect. Imagine that you took an orange peel and then you smashed it down on a table. It can't stay working. In particular, you have to choose what gets distorted, and you have three choices. You can't have all three of the area and the angles and the contiguity relationships correct. One of them has to be wrong. In a lot of map mapping, it's a trade-off between the area being correct and the angles being correct. But there's also this third possibility, which is, well, is it all contiguous or are you allowed to have interrupts? So you see on the bottom are maps where you don't have interrupts. Everything is contiguous. And in some, the area is equal, and in others, the angles are equal. Whereas on the top, you've got this approach, and this particular one is called Gore map. And notice how we give up on having everything be contiguous. There's actually some interrupts in that mapped projection of a unbroken 3D surface. So the Mercator projection is a very well-known one, and it was designed to help people navigate ships. So the angles are correct. You can draw lines on it, and they actually correspond to a straight line that is an arc on the Earth's surface. But the areas are wrong. It distorts the size of the country. So if you're navigating a ship, that's not a problem. But be aware that if you're trying to understand spatial relationships, it gets more and more wrong as you go from the equator towards the poles. Given how continents are distributed on planet Earth, that means it's more of an issue in the north as you get closer to the North Pole. Antarctica is also quite problematic, but that's not as big of an issue for most people. So be aware that the Mercator is an example of a map that does not have correct areas, although it does have correct angles. Now there's many, 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 many map projections that have been proposed. Here's two sites that let you play around with some interactive ones. Um, the Jason Davies maps have been, a lot of them are integrated into D3. D3 actually has built in a great number of map projections. So very, very easy to do different projections in D3. And there's also a nice demo from Nico Belmonte showing this so-called myriahedral projection that focuses on the ones that also have a lot of different interrupts and lets you see different versions of projections in that way.